Hello, everyone, and good morning or good afternoon, wherever you are. Hope you're having a great day wherever you are. I do appreciate you joining us for this new and live webinar brought to you by T&D World. We're excited to talk about protective technologies for underground and offshore transmission, distribution, power cables. Our webinar today is entitled Reducing Risk of Operating Underground and Subsea Power Cables, and it is sponsored by Synaptech. This company is a global leader in power system instrumentation expertise. My name is Rod Walton. I'm managing editor of Energy Tech and Microgrid Knowledge. I am representing T&D World today as we are all part of the energy industry coverage with Endeavor Business Media. I'll be your host for today's webinar. And before I introduce our speakers from Synaptech, let me explain how you can participate in today's webinar and in our platform in the most seamless way possible. First, if you're having any technical difficulties, and I hope you can hear me, just look for the question mark icon that's on the side of your platform screen. Click it, type in your problem, and hit submit, and our technical expert will help you out with that. We also recommend that you disable any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar platform. Additionally, we welcome your questions during today's event. Saul, Stephen, and Tobias will answer as many questions as possible in the Q&A session that follows their main presentation. But please feel free to type your questions in at any time. All you have to do is find that question mark icon that I mentioned earlier, hit or type in your query, hit submit, and you'll be in the queue. Please be aware that today's session is being recorded and will be available on the T&D World website within the next 24 hours. That's tdworld.com. You'll be notified by an email when that archive is available. And once it's archived, we'll also make available a PDF of today's slide presentation that will be in the Event Resources tab. So now I'd like to introduce our speakers and set the tone for today's main event on how to avoid power cable failures in the underground and subsea projects. Saul Matthews is Vice President of Sales at Synaptech. He brings 30 years of experience and has led growth for brands in IT, mobile, unified communications, and semiconductor industries. So he has deep experience in various technologies, as you can see. Saul is joined by Tobias Singh, who is Applications Engineer at Synaptech. Tobias is one of the leading lights of the new generation in O&M and cable technology engineers. And finally, we have Stephen Blair, who is Vice President of Applications at Synaptech, and he leads Synaptech's product strategy. So you're in great hands with these three experts. So now I'm going to turn it over to first Saul Matthews, Tobias Singh, and Stephen Blair. Saul, it's all yours.
Hey, thank you very much. And so good morning or good afternoon, everyone. And thank you for taking the time to come and listen to us today. We're going to take you through some slides here, which I'm just going to click through. And of course, Tobias will be on standby behind the scenes, managing responses in real time to any questions and answers you've got. Our agenda today is to take you through very quickly who we are, because this might be a new name or a new company for some of you. We want to explain where we fit into the grand scheme of things and what industry challenges in particular we address relating to the operation of power cables. Part of that is to also explain how our technology works, and then look at some of the specific applications and how our technology yields results for the operators of power cables. And Stephen will take you through that detail. And hopefully at the end, if we weren't able to answer questions in real time on the typed responses, we'll be gathering those up and trying to play them back to you. So very quickly, who we are. I know every company has to start with this one, but we actually founded our company 10 years ago. And of course, it does take 10 years to become an overnight success, but we are actually operating a business out of the west coast of Scotland. And you can see that lovely picture of us up in the Lochs in the Highlands, which of course is on the one day of the year where it is actually sunny and not raining and miserable over here, because it's pretty cold and wet today. But based in Glasgow in Scotland, we are the developers of a technology that we've kind of dubbed distributed electrical sensing, or DES. And that, in essence, is the technology we invented where you can measure any kind of voltage or current without the need for buildings, power supplies, or data networks. They're totally passive sensors that are networked over a wide area using light itself through optical fiber rather than using data networks or 4G, 5G networks or any kind of data outside the substation. And this ability to reach out beyond a substation fence and monitor and instrument remote but high value assets like power cables is critical these days, and we'll take you through why. But fundamentally, our projects have been centered in the transmission, so high voltage power industry, some of the higher end voltage ranges of the distribution networks, and also offshore wind, where we are either helping developers and operators reduce the fundamental capital cost and the carbon footprint of instrumenting complex power systems, or we are being used to either avoid or reduce outage time and repair costs. And you can see some examples of some of our customers along the bottom here. It's a mix of transmission operators and offshore wind developers. So fundamentally, I don't think anyone is surprised by this slide, because this is a universal thing that's happening in the power industry. We want to decarbonize, we want to embrace and integrate renewables, we want to decentralize that generation, and we want to take advantage of digital technologies. So while the industry tries to repurpose this old established infrastructure and integrate renewables without causing disruptions and disturbance to the stability of the grid, availability and resiliency are critical, and we don't want to do it in a way that's risky or endangering any life. We've realized that this is a great time to put more eyeballs, more sensors out into these decentralized remote areas of the grid, as I said, leaving the substation and looking far away, to instrument the network in real time and give better visibility and control to this decentralized world. Basically, as the transition happens, it requires more distributed measurements, and that's what we provide, because again, we don't need things like buildings, civil works, supply of power, or data networking. And very generally, we can say that one of the limitations today on conventional monitoring techniques, imagine you want to measure something 20, 30 miles or 40, 50 kilometers away from the substation. Maybe it's a new grid connection from a wind farm or a solar farm. Maybe it's a very important new grid connection for a hyperscale data center customer. But whatever that remote connection is, it's very expensive, and it turns out you need buildings and power supplies and copper wiring and merging units and data networks simply to go and acquire some critical measurements like a voltage or a current. So if you can avoid the need for those power supplies and copper wiring, if you can eliminate completely any active electronics or moving parts so that you never need to maintain or recalibrate these things, you're going to save money, and you're going to save time, because you don't need permission to go and upgrade or build new substations at these remote points. So there's a big capital cost saving and time saving in deploying our technology. That's normally what it's used for. But very specifically for the operation of power cables, we've noticed, in fact, most of our business centers on the challenge that for whatever reason you underground a cable, or you have to cross a body of water perhaps to connect things with these high voltage power cables. They're vital. They're critical assets, and yet they're completely invisible. They're very remote. They're very inaccessible. They're literally hard to go and inspect and check and maintain. And all of the conventional, traditional monitoring techniques that are out there for monitoring these cables have limitations. Many of you will be familiar with things like distributed temperature sensing or distributed acoustic sensing. So distributed temperature sensing is when you're monitoring along the length of the cable and looking for changes in depth of burial, which might indicate a cold spot or a hot spot and a failure of the insulation. DAS is typically for third-party intrusions. Something or somebody has hit your asset or damaged it and caused a failure. Maybe some people are using ROV inspections with remote submarines to monitor displacement and change in the soil conditions of the seabed when the cables are running under the seabed there. We've talked to customers who are experimenting with online PD monitoring as a potential way to identify damage or impending faults in the cable, or it's just manual inspection. All of these things have a couple of things in common. They're expensive, and they typically give you a lagging indication of some kind of insulation failure. With the exception of DAS in subsea, for example, none of these technologies has ever been able to predict or avoid a failure. They tell you something has already failed, and they are monitoring the result of the problem. The cause of the problem and where the problem surfaces is actually something that we address very particularly. And one thing that these things have in common, apart from being somewhat late in being able to identify problems, is that they miss one of the key locations of failure in power cables. And this isn't from us or our data, and we'll show you later where this comes from. It's DNV data that's been shared in the GCAB conferences around the world several times. It's very typically the joints, terminations, and link boxes where you see failure occurring. And because of that, it's critical to put our kind of sensors in those locations because they're small and passive and they fit, and because DAS, DTS, and these other visual inspection methodologies actually miss the location completely and can't see them. So you don't see something coming and you haven't got time to avoid it. But before we go too much further, we wanted to stop ourselves at this point, having established that power cables are at risk and perhaps some of these monitoring techniques aren't providing a kind of analysis of the causal problems that result in these kinds of failures. We wanted to check in with everyone and run a little quick poll here. So as I mentioned, that Tobias is going to pop up a poll for you. So we'd like your opinion on some of these challenges. So as these questions come in, we'll be able to send the results to you all in a moment. But of course, what we were interested in is the risk mitigation strategies behind the operation and maintenance of power cables. And we've given a range of options there to find out if there's some consensus across this big audience today of what matters. And I think I'll give it a few more seconds because voters are still coming in and polling, so I don't want to prejudice this. But if I were to maybe allow it to think, I'd stop there because there's not too many more people coming in. So there's an interesting spread here where the most relevant risk mitigation strategy is some kind of optical condition monitoring, followed by online partial discharge monitoring, followed by regular offline partial discharge monitoring. And I think that's a pretty interesting difference because when we have been talking to customers around the world about the challenges of operating power cables, I mentioned before this pie chart you can see here where roughly 69, let's call it 70% of failures occur in joints and terminations that are unseen by the optical sensing techniques like DTS and DAS. They actually don't see those locations. And where they are focused is on the 31% of the cable insulation itself, where there could be a failure. We've realized that one of the key insights is that if you can understand the combined effect or the correlation of electrical and mechanical stresses and some environmental stresses at these locations, you can see the early warning signs or the precursors to failure that are evident. And we're going to take you through that today with the help of Stephen and Tobias. So to get to that, we have to explain how DES works and what distributed electrical sensing is. And I didn't want to spend too much time on this today, but I'll give a very quick overview. And if this provokes interest and questions, maybe we can follow up with people who have got more in-depth questions afterwards. But think of it as an IEC standards compliant device that goes into a substation where you've got power and communications. And then we use the optical fiber that's available in the OPGW or alongside the cables to reach over the fence somewhere very far away and monitor remote assets with passive sensors that are multiplexed or serially distributed along that run of optical fiber. So we can reach per fiber channel something like 60 kilometers or about 40 miles along that fiber and measure up to 30 locations simultaneously and at the speed of light. It's light itself going out of the substation and back. There is no data outside the substation fence, only colors of light. And from that, we can measure any combination of things like current, voltage, temperature, vibration, strain. And that's why we get used for a whole combination of applications where this is actually a protection class system. So normally what we're doing is looking for faults in complex circuits and either tripping or helping the protection scheme to locate the faults in section and provide a more kind of granular and targeted post-event response to a fault. But when we're not clearing faults very rapidly, which is a great feature of this technology, we're permanently synchronously monitoring all these locations, looking for interesting correlations that would give an early warning sign of a problem. And that's why when we look at all the different applications that we've got, it falls into, yes, we do some digital substation work and busbar protection and complex feeder protection. Yes, we've done some work with integrating renewables and speeding up grid connections and facilitating and reducing the cost of instrumenting them, fundamentally upgrading from distance protection to unit protection. But when it comes to remote assets, we've done work with overhead lines and underground cables where we're monitoring the condition and looking for those warning signs of problems that are coming up, most dramatically so in offshore wind, when even one cable fault could cost 3 to 4 months of outage and tens of millions of dollars to repair. So with that thought, we wanted to take you through the next section, and I'll hand over to Stephen to explain how this technology specifically helps to identify these failure precursors and delivers insights that will allow for either avoidance of an outage or at very least optimization of scheduled maintenance and possibly even real-time thermal rating improvements. So Stephen, can I pass over to you, please?
Yeah, thank you. Thank you, Sol. Okay, so I'm going to take you through some of the technical details here and hopefully explain how this platform that Sol has introduced, how it can help us provide some quite critical benefits for monitoring cables. And this is applicable to both cables offshore, where they're deployed for wind farms, but it equally applies for onshore as well for high voltage grid cables. So I'll provide a bit of information about how this works. So to get started, as Sol explained, DES is our term for providing a kind of a new visibility of cables, and it's a combined visibility of both electrical and mechanical parameters of these assets. So it's really appropriate for long linear assets such as cables, where you are interested in looking at things at multiple locations along the length of that asset. So what that gives us is it gives us the ability to find degradations to the health or the performance of those assets, thanks to being able to put sensors where they're needed. And previously, with other technologies, it's really impractical or not cost effective to achieve that. So ultimately, what this gives us, it allows us to find precursors of damage early, and that's the key thing. And it can also be used to predict the likelihood of failure of these critical assets, and ultimately this gives operators significant cost savings for their maintenance. So that's really what we're trying to achieve here, is saving operational costs for operators. So moving on to the next slide, this gives a bit of an overview of how we achieve this. So in summary, we take several inputs, such as our own deployments, looking at electrical measurements at different points, temperature measurements at different points, And we can sort of optionally augment that with other data sources, such as DTS, DAS, and other information that's available. And we process that data using our cable monitoring solution, which includes like an outlier detection engine. So this provides visibility of damage progression in these assets over time, and we can use that to provide intelligent alarms that expose some subtle failure modes that are really not accessible or possible to achieve using conventional measurement approaches. So again, what this leads to is helping the operators reduce their maintenance costs, because we're providing early warning of issues that may become catastrophic in the future, but by providing this early warning, we make it the maintenance much more manageable and cost effective. So moving on, here's to make things a little bit more practical and kind of clear about how we achieve this. So this is one way of how we would measure a typical joint in a HV grids system. So you can think of this like a typical link box for a high voltage cable. And what we're doing here is we put CTs around the coaxial cables that go into the link box, and then we our passive sensor technology to the secondary output of those CTs. And this allows us to collect the measurements. And as Saul explained earlier, this is all done completely passively, so there's no power supply needed at this link box. It's purely passive CT on our kind of converter box, basically. So what we can do is we can do this at multiple joints along the length of the cable, and this kind of automatically gives you several kind of immediate benefits. So one example of that is about you can use this measurement approach to detect flooding of the link box, which is a fairly clear kind of, perhaps not failure mode, but something the operator would like to know about. Or there are also various kind of short circuits of the grounding approach, which can be detected when you have this kind of degree of measurements available. So this is kind of unlocking some measurements that were previously not available because it's basically impossible or very expensive to get measurements in these locations. So that's what we make available. So what's the bigger picture here? So this slide kind of analyzes or summarizes our analysis methodology. And what we're saying here is that the key point is that by using this distributed sensing approach, we can intervene at multiple early stages before the asset actually fails. So that's in everyone's best interest, basically. So what we do is we can do things like model the loading of assets over time. And there are also various types of asset damage that we can detect directly or through secondary effects such as reduced performance of those assets. So those are some of the early warning signs that we can pick up. And then we can also monitor discrete pathways for electrical stress and thermal stress, should they occur. So these are more advanced degrees of asset failure. Well, before failure, but getting towards failure that we can pick up through various mechanisms. And so again, we have the tools to detect these issues early, and there's multiple layers here basically to provide backup as certain failures advance. So moving on to the next slide. Here's a bit more technical detail about what is actually going on here and what we're actually doing. So we've done a bit of analysis of the kind of literature that's out there that expresses how to diagnose and locate issues with cables. On this slide, this is focused on the offshore wind kind of context, where typically solid bonding is used for grounding the earthing scheme on that system. So I won't go through this in much detail. The summary here is that there's various discrete failure modes or damage modes that we can detect and do useful things with the kind of discrete monitoring. Here's a very similar slide, but this is tailored for grid-based high voltage cables. So they typically have a different kind of bonding scheme for grounding the screen of that cable, and there's typically cross bonding used. So that makes things a little bit more interesting about what we can kind of figure out. So that this opens up some additional failure modes that we can figure out, as I mentioned earlier, about flooding in link boxes. So that's something that can be detected automatically for monitoring of screen currents. And here is a little bit more detail that I won't cover all of this for the sake of time, but this is some of the kind of academic background about what we're doing here. So basically here we're summarizing the process of an asset failing through multiple possible different pathways. And if I take one example here, just to make it a bit more realistic and practical, if we look at row 3 here, which mentions grounding defect short circuit, it's actually fairly trivial for us to detect screen bonding issues simply by monitoring the ratio of the phase current to the screen current or the sheath current. So that's actually a really useful tool for us to monitor and use because it really highlights common installation problems that can occur, or if something degrades over time, then that can be apparent through this metric of the ratio of phase current to sheath current. So it's something that's dead easy for us to calculate because we put the measurements in the right place and we bring it back to a central location, and then we can summarize that over the whole asset and basically quite readily give the operator some warnings about what's going on. And it's very straightforward for us to find outliers in this kind of metric. So our goal here ultimately is to provide a combination of the normal kind of status quo of kind of periodic offline measurements and merge that together with online real-time measurements and sort of bridge the gap basically between servicing assets, which is done periodically, and filling in the gaps there. So we think we've got an overall solution which can do that. So basically you go from your commissioning, where you do tan delta tests, you do partial discharge offline testing, where you really stress the asset and find any weaknesses. Typically that's not really an issue because the cables are of decent quality generally. But when the system's online installed, all the joints have been made, all the terminations have been made, that's where Synaptics technology can kick in and provide you online visibility of these potential hotspots for problems. And our goal here is to provide the best kind of through life cable protection, basically, and observability. So just want to also briefly mention, I mean, some of you in the audience who are no doubt well informed in this topic are probably already thinking about partial discharge or PD. And how does this compare? Where does it fit in? So there's a lot of detail on the slide here, but just to summarize, partial discharge is indeed a very useful tool when you can do it offline. And that's the key point, is when you do it offline, when the cable is disconnected, then you can ramp up the voltage to, typically about 3 times nominal voltage. And then you can really stress the asset and find if there's any weaknesses. But obviously, once the system is operating and has been commissioned, and the voltage that the cable is exposed to is going to be nominal most of the time, apart from, during any surges or switching or that kind of thing. So that means that partial discharge has limited value during online scenarios, which is, most of the asset's lifetime. So we believe our technology can fill that gap and provide some critical intel about the health of the asset during its online lifetime. Partial discharge is typically going to provide late information. If you did monitor online, it's only going to trigger really when the asset has already failed or is very close to failure. So that's kind of the unfortunate aspect of partial discharge monitoring. So, and we also believe that the DES approach is much more convenient to install and maintain over time because of its passive nature. So I think the next step is for me to stop talking for a little while, and we're going to do another poll. So hopefully that's active for you now. So thank you for your answers so far. We're just bringing up the results, which are coming in.
I think that's it for you, Stephen. There's no more new people coming in answering there. So the clear winner is the lost revenue to outage.
Yep, that makes a lot of sense. Yeah. So, and again, that's lost revenue due to outage is exactly what we're trying to target to avoid, because we want to make sure that these assets are being worked appropriately and delivering, particularly for offshore wind, delivering renewable energy into the grid. Okay, so just to, as a final couple of points, really, I just want to explain about a deployment where we've used this approach already, and some kind of early results that we've got that kind of show the potential for this. So I want to kind of really make this seem like it's real and show you a genuine deployment of this and where it's delivering value. And so we have a deployment of our technology in Spain on a 400 kV circuit. So this is an AC circuit, which is underground. It's a tunnel which goes about 12 kilometers underground, and we're monitoring several of the sections of that cable. And this is a very critical cable that delivers power to one of the main cities in Spain. And what you can see on the slide here is just what you get by default from our sensor systems. You get waveform data. You can see on the bottom left there, that's the phase currents that we're measuring. And also we monitor in detail and provide harmonic information as well. Sometimes that's quite useful. So actually we found an instance where one of the CTs was saturating because the current was so high, so we were able to recognize that pretty readily through the monitoring approach, and ultimately that CT can be replaced with a different rating of CT. So what we've done here is we're monitoring screen currents or sheath currents at multiple joints along the length of the cable, and also at the termination of the cable where it converts from overhead line into a cable. And we're also monitoring temperature at point locations along the length of the cable. So that gives us quite an interesting picture of the whole kind of everything that's going on with that cable at discrete locations where it's really important to measure it. And like we know for high voltage cables and grids, I think it's about 57% of outage time is due to the joints or terminations. It's due to issues at those locations. So that's exactly where we're targeting our measurements to give this kind of much needed intel. So here's just an overview of what we can look at in these systems. So on the kind of top left is kind of our dashboard view of kind of, that's a generic view we use for any type of system. On the bottom left, it gives you our cable specific view, which gives you a visual indication of everything that's going on that cable, every sensor at the same time, and we can highlight alarms when relevant. We can also pick up metrics there, like I mentioned earlier, about the ratio of phase current to screen current. And that's quite a powerful metric for identifying failure modes, as I'll kind of hopefully emphasize in a moment. And then on the right, you have these three plots that show some real measurements from that system during July this year. And on the top is the phase current over time. And you can kind of see this is about eight days of data, and you can see there's a kind of pretty typical kind of daily load cycle on that circuit. And in the middle is the sheath current measurements at various locations. And then at the bottom is the ratio of phase current to sheath current measurements. So we can go a little bit deeper on this and start doing a bit of what is honestly quite straightforward analysis. You know, we don't have to really resort to anything kind of exotic or complicated to give operators useful information from this. We can do some simple clustering of data and then apply some outlier analysis, which is really just doing statistics on the data. And we can tell operators where things are performing outside what we expect. So in this example, you can see we're clustering the data and we're looking at different parameters here. And what's probably obvious is the orange cluster of data is generally different to the other locations. So that means location 2, which is the orange data, it's doing something a little bit weird compared to the other locations. So that gives us a cause for perhaps caution about what's going on at that location. And maybe there's some maintenance that can be targeted in that. You know, what we're seeing also is it's not urgent, but this could be something that trends up over time. We're looking at that analysis at the moment of what the circuit is doing right now. So this just gives you a flavor of the kind of power of what we're doing here. We're looking at multiple variables and kind of computed variables as well. And when we combine that by looking at a wide area, we can figure out if something interesting is happening and something that we need to build an alarm from. So this is like a totally new category of alarm that's never really been possible previously, because the visibility of the system isn't hasn't been available. So really, just to summarize then, what we're trying to do here is we're trying to avoid the system operators having to spend a lot of money and a lot of time and a lot of human power in doing what is typically, manual periodic inspections of these assets. So we want to provide some tools that automate that and do it cost effectively, particularly when you're thinking about underground towers, underground tunnels in grids. These are very dark and unpleasant and unwelcoming environments that, previously people have to walk down to manually inspect these assets and do, maybe thermal imaging to understand if the joints are healthy. And also for offshore assets, it's extremely expensive to charter a ship and find a correct weather window to go and do maintenance. So we're trying to displace much of these expenses by providing proper visibility in real time. And also, as the survey revealed, this seems to be a popular thing to do. We want to minimize the downtime of these assets so that they are, particularly for offshore wind, so that the generation is maximized and the operators are not losing money, basically, by having to take things offline to do maintenance. And just to emphasize again, we're trying to get in as early as possible to find these defects and resolve them, or at least flag them as potential issues, so that the operator can best optimize their kind of intervention strategy. So I think that covers everything I want to say. Yeah, so basically we're trying to, I'll hand back to you, Saul. Thanks.
Sure, thank you very much, Stephen. So just to kind of zoom out for one moment and give everyone some perspective here, we do have some backup materials if people have got particular questions about other case studies or deployments that we can show. But the concept of applying distributed electrical sensing to these power cables, whether they're subsea or underground, is that we fundamentally want to, if you forgive the pun, shine a light into some dark corners to expose problems and buy the operator or the asset owner some critical time to do something about it before you get to the point of failure. And particularly if it's subsea or it's in a really difficult, inaccessible place, we'd like to be able to give days or even a week's worth of data so that you've got the time to organize that intervention and you know why you're going out there and what you're looking for. So our technology is very useful for either fundamentally reducing the capital cost of instrumentation or putting visibility and control into locations that were not possible before. And from that, you get fundamental savings in operational cost, because we're either going to avoid an outage, or as Stephen said, we're going to use that data to optimize scheduled maintenance, go and visit a particular site because we've seen something going wrong, not because it's Friday afternoon. And this all comes together as a fundamental safety and risk mitigation strategy. If we can mitigate the failure risk, we can operate these assets better. And within that concept of operation, it is actually possible to use some of these finer measurements, such as the point temperatures on the terminations or the sheath currents, to optimize real-time thermal ratings and give an entire systemic view of how can I optimize the throughput of these assets in a safe manner. And then at a very, very long scale, as you can see, we build up these data histories that Stephen was showing you from that example there from our transmission customers, where you're collecting data over the lifetime of the asset. And probably one of the most useful things we can explain to everyone today is this idea of, and I'll give you examples, one of the world's biggest offshore wind farm is now in development in the North Sea, so to the right-hand side of the UK, a very inhospitable sea environment. It's 100 miles away from the coastline, where you've got, I think, 400 kilometers of cable. So for something like 300 miles of cable, I think there's 114 different cables out there, and we are monitoring every single cable permanently and synchronously for the 30-year operating life of those cables looking for the early warning signs of a problem, because then you've got the ability to do something about it before you have a failure, which it always costs millions. Literally about $10 million would be a typical cable failure cost in offshore wind operations today. So if you've got the eyeballs out there to see what's going wrong, and you can find out when, where, and why, that's great. You're either looking at all of those cables and saying, well, which one's the exception? What's the rate of deviation from one compared to the others when they should be the same? Or you're looking at one of those cables and saying, over its life, under different environmental conditions and different load scenarios, is it coping? Is it degrading as we expected? Is it still going to last the distance? And you get better data for making lifetime asset management decisions with this tool. And I think Stephen slightly touched on it, but I want to emphasize, we are not saying that DES is the only way to monitor a power cable. What we're saying is, when you combine this additional visibility of all those waveforms and all the detailed electrical stress measurements with the mechanical ones like DTS and DAS, and you put it together in one holistic system, you've got a better overview of your asset, how it's operating, how it's degrading, what's going wrong, when, where, and why. And perhaps most importantly, you are de-risking the operation and having a much higher confidence in any alarms that come up. I think many of you will know that false alarms can be a very frustrating. So if you're able to improve availability and resiliency and reduce safety concerns whilst improving your control, I think that's the ideal solution. So we hope that that overview makes sense, and it at least provokes some thinking in the audience here about how you could very simply install these systems new, or by the way, we retrofit these systems quite often to give that additional sense of security and control on these critical assets, which otherwise are somewhat out of sight and therefore out of mind. Now, at that point, with only 10, 12 minutes left in our presentation today, we wanted to make sure that we had the chance to go through the Q&A session and address some of the most popular questions that have been coming up in the background for everybody. I know Tobias has been very diligently trying to answer some of them, but perhaps for the people that are online and can ask, we can pick out the most important questions and go to some of the answers or give you other examples of what we've been doing here to see if it's relevant for your business or your particular operational needs.
Sounds great, Saul. So yeah, we'll pick it up from there. I mean, great job, Stephen. And as you mentioned, Tobias doing a lot of work behind the scenes. It's really critical to hear all this and be enlightened, no pun intended, on the most common places and ways of cable failure. And you're right, we have a ton of questions from our attendees, and we want to get to as many as we can. And I think they mentioned up front that those they don't get to, they will try to get to later. So I'm going to just start out with a basic one, though, that comes up. And the question asks is, how can we set threshold alarms?
I'll give you my dumb answer, and maybe Stephen can contribute a much better, more technical answer. One of the classic ones that we've experienced is if you can basically monitor the phase current at a termination and you can provide a spot temperature of how hot that termination is running, then you can instantly see things like ohmic overheating. And that's a pretty simple alarm threshold to set. If you've got a low current and a high temperature, that's about to explode. And we can instantly see that and warn. And then we can have a sensible conversation with the customer about what level to set that up. But it's not the absolute temperature on its own. It's not the current on its own. It's the correlation between the two that matters. So things like ohmic overheating because of water ingress or imperfections when you're jointing, that can suddenly surface and we can directly see that. So sometimes it's screamingly obvious how you should do it. But Stephen, perhaps you should give a better answer in terms of how synthesis can be set up and how we can establish these things over time, as well as by agreement with the customer.
Yeah, so there's some things that are fairly obvious to pick out, like, if a temperature is beyond a threshold, Absolutely, we can flag that as an alarm. But what we're really trying to search for here is some things that are a bit more subtle and were previously impossible really to derive, because you couldn't have the sensors in the right place. So as I mentioned, being able to look at sheath currents in multiple locations and phase current on perhaps different array cables in the offshore wind context, and temperature at all these locations. So what we can do is, with our outlier analysis approach, it means we can look if any individual sensor is doing something weird that it doesn't normally do, that deviates from its normal statistical behavior, then we can flag that. And we take care to make sure that we remove seasonality effects that are normal. So obviously there might, for a high voltage grid cable, like I showed earlier, there's a cyclical nature to the load on that cable over a day. And there'll also be different variations throughout the seasons, throughout the year. So we take care to subtract those benign, normal variations from the behavior of the system to be able to detect what's a true anomaly. What we can also do is, as well as looking at each individual sensor and what it does over time, we can compare one sensor to its peers and see if, for example, if one temperature sensor is doing something strange compared to a similar sensor at similar locations, then we can flag that as an anomaly. So that's our approach, is that we're trying to do something new here and expose a different kind of class of alarms that were previously not possible, really.
All right. Thanks, Stephen. Great answers. So this question comes in, and it basically it starts asking about for the insurance, and the attendee asks, "Do you mean a risk mitigation strategy from insurance without any inspection or monitoring actions?" Hope I asked that right.
Well, maybe I can take that one on. Power cable failure has plagued the offshore wind industry since it started up. There are simply too many power cable failures, and they're unplannable, unknowable in advance. They just happen. And insurance underwriters and reinsurers are getting very frustrated about this, and they're threatening to walk away from the industry. It's a huge challenge. Now, we cannot say, here's my technology, this will guarantee that you get 10% off of your premiums, though, because the insurers just don't work like that. But what we have been able to do is work with developers and operators of cables to say, okay, if we are taking a proper risk analysis approach or a methodology to the installation and the operation of these cables, if we can ensure they're installed correctly, if we can ensure there's no poor handling, if we can test them correctly, and if we can correctly monitor deviations from that initial state during operation, we can show that we've mitigated risk. We can't zero the risk, we can't avoid the risk, we can mitigate it. And when we go together with that asset owner operator to the insurers and say, look, we've gone the extra mile here and we can avoid, literally dodge some of these bullets, there are huge cost and risk savings involved in this. As I mentioned before, it's not uncommon to hear about a repair campaign cost in offshore wind going from $5 million to $10 million plus. This is just the repair campaign, not the loss of revenue, just the repair campaign. And it's 3 to 4 months in some cases before you can get this thing fixed and put back together again. And the insurance premiums are severe, right? You're paying for the first 60, 90 days, and then the insurance kicks in. If we can show the insurer that we can reduce that risk and we're taking better measures to see these problems coming and avoid them, our technology would actually pay itself off the first time you avoid one of those risks. And at a 1 gigawatt scale over 30 years, you're probably going to have somewhere in the region of 12 to 15 failures like this. So if this system pays itself off in the first time round, and you can talk about reduced terms with your insurer, it's a very powerful tool. We can't do it on our own. We have to do it hand in glove, holding hands together with the asset owner operator to figure out how we can make that happen. But it is a significant risk mitigation strategy to have active monitoring in the place where you have most failures and giving advanced warning or a preventative measure on those failures.
Yeah. Sounds well worth the investment there, Saul. Well, so I'm going to follow up with this question on how accurate is the location prediction of a defect?
Maybe I can answer that one. Yeah, so we are able to monitor on sections of cable. So for the electrical faults that we look for, we're looking at faulted sections of cables. For defects and things like that, for the thermal side of things, we're able to get a lot more granularity. So we can look at the point temperature sensors on each of the terminations. Those are very tiny. Those are a few centimeters in size. So we get a spot measurement there. When we combine with DTS, distributed temperature sensing, we can typically get resolutions down to 1 or 2 meters, or up to several meters if you have a very long range system. So that means that if you're seeing hotspots in your cable, you'll see them coming much earlier. That DTS system also likely has an OTDR, optical time domain reflectometer, which means that you can look for breakages in the fiber or points in the fiber that's actually broken down if you have a really severe cable failure. So if you see that there's a breakage somewhere along that cable, you can then diagnose afterwards that that cable has failed somewhere along that route where you see that breakage in the fiber. Hope that answers the question.
All right. Yeah, thank you for that. Our next question comes from an attendee who asks, we have a complex 15 kilovolt distribution network that feeds 100+ buildings. How do I find out if this is economic or a good fit for our system?
I suppose from an economic, sorry, I can't even say that word, from an economic perspective or a cost perspective, this is probably the best way to deal with that complexity, because any other manual or inspection regime or automated distributed sensing process like partial discharge monitoring, you're going to have to go and put sensors and servers and data networks and power supplies at every point. It doesn't scale very well, but fortunately, the way the architecture of our system is designed is that you have one box centrally looking out at many locations. So my analogy to that example is on some very big wind farms that we're now being deployed on that have hundreds of cables. We're deploying thousands of sensors and permanently and synchronously looking for outliers and exceptions so that you can get a targeted response and figure out where to go and why to deal with problems as they arise and get the earliest possible warning of these issues as they arise. So I think ultimately it would depend on what is the relationship between the cost of our system and the ongoing cost of data management and warnings and alarms versus, well, what does the outage cost? And that very much depends on who's at the other end of that load and why they want the power. If you were at a transmission level, it's evident. If it's at a huge manufacturing level, then outage and production loss is evident. I think it will depend on this particular business case, what the maths of this is. But fundamentally, if you want to understand if your cables are withstanding all these cyclical stresses and environmental stresses, this is the way to catch it before it becomes unresolvable and runs away from you. So the maths really is about the cost of the outage to the end user.
Yeah, I got you. Well, and I just want to alert you guys and the audience. We're basically a minute up to the top of the hour, but we're going to ask 2 more questions because we have a lot of them here, and appreciate that you guys are willing to try to crack into some of those other questions that we didn't get to later on. But so this question asks, it appears that this system really needs to be implemented at the time of initial installation of the underground system. But they go on to ask, how can this be implemented to existing underground systems?
So my quick dumb answer to that would be If we're measuring things like spot temperatures of terminations, or we're looking at sheath currents and phase currents, fortunately, we use industry standard primary devices. It's a current transformer, and you can get split core ones, that kind of go around the insulated cable near the cable sealing end, and they're very quick to therefore retrofit and install and splice into the existing fiber network. We've timed this stuff, and we can do it very, very quickly. So it does not have to be done when you're initially laying or installing or commissioning the cables. Sometimes that can be an economy. Actually, sometimes it can be a false economy to try and do that work at the same time. But it requires no new skills or training or expertise to install our sensors, because we're using very industry standard devices that are non-invasive and don't have to go through the insulation to measure currents and temperatures. Voltage is different, and you'd have to use a VT, but these are standard CTs and standard VTs that we use. The sensor is a passive device that's on the secondary side that's built into it, running off of the copper secondaries from these transformers. So it's actually very easy to retrofit, and we've done it several times.
Well, that's good to know. Thank you for that, Saul. I'm going to end with this question to take us home here. While plotting the condition of the cable, is it possible to forecast a critical failure timeline?
Yep, that sounds like a good one for me to jump in and give an answer to. So yes is the short answer, and we have done this for some of our installations. So some of our a system that we've retrofitted in the kind of sort of northeast of Scotland here on a wind farm, where we're monitoring a couple of export cables going out into a wind farm. And what we've done is we've kind of done the analysis work on basically figuring out everything we've learned from the data, and also we've applied a bit of forecasting capability to that. So right now that's a sort of an offline capability that we have, and something we will build into our kind of real-time online pipeline of data processing in the near future. And that will capture a few capabilities, such as like real-time thermal rating of these assets, particularly taking into account the detail that you get from the sheath current measurements, because that can give you a lot of information that you don't necessarily get from conventional ways of doing this. So the answer is yes, and we're working on that type of system to deliver that in the near future.
All right, thank you for that, Stephen. And with that, I'm afraid we've run out of time, but don't despair. They will try to get to as many of those unanswered questions as they can. And also remember that this live event has been recorded and will be on demand, available probably within the next 24 hours or so at tndworld.com, tdworld.com. And once it's archived, we'll also make available that PDF of the slide presentation in our event resources tab. It will be available for about 6 months, the whole presentation, after this live event. So please feel welcome to watch it again and share it with coworkers and friends in the industry. And we always appreciate it when you do that. And with that, I'm going to conclude today's presentation on reducing risk of operating underground and subsea power cables. And on behalf of T&D World, I'd like to thank our sponsor, Synaptech, and our excellent speakers today, Saul Matthews and Stephen of Synaptech. We also had Tobias Singh, who was in there to help kind of behind the scenes and answer a question there for us. Fantastic job, gentlemen, on mission critical operations that are just growing in importance and mission criticality all the time. So thank you so much for that. And thank you to our audience for attending and for your questions. We all learn from each other, so we appreciate those. And with that, I'm going to end our webinar presentation. I'm Rod Walton, Managing Editor for Energy Tech and Microgrid Knowledge on behalf of T&D World. Thank you for joining us, and hope to see you on another webinar in the near future. Have a great day, everybody, and goodbye.